21058 and our project is sponsored by Raytheon Technologies.
We are tasked to design and build a robotic system that autonomously torques fasteners on a plate in a specified order and torque to a specified value. There exists a variety of automatic torque tools. Nevertheless, Raytheon relies on manual methods as they find the available automatic tools to lack the control and accuracy they require. When looking to produce an autonomous system, robots are commonly good at automating repetitive tasks. However, they commonly struggle when their environment or operational demands lack consistency. We are tasked to overcome these challenges and produce a system that can easily adapt to handle a wide range of torque operations. However, the most challenging aspect of our project is the task of autonomously aligning the socket bit with a fastener to ensure that proper engagement is achieved. This is because the accuracy needed to complete such a task is approximately 5 times greater than the accuracy of the specified fastener locations. This means our system cannot only rely on absolute positioning accuracy. It additionally requires there to be an intelligence component that allows the system to make unsupervised decisions in real time. Therefore, we implemented a machine vision solution to overcome this challenge. Our system uses a 3-axis gantry rail system, similar to a CNC router, which uses stepper motors to provide motion in 3 degrees of freedom. On board the gantry, we have what we call our torque mechanism and camera assembly. The torque mechanism is composed of components responsible for applying and sensing torque. Components include a DC motor, a gearbox with a 201 gear ratio to decrease the RPM and increase the stall torque, and a reaction-style strain gauge torque sensor. The camera assembly includes 2 Allied Vision Aviom cameras, each with a lens illumination ring and a 3D printed camera mount. A graphical user interface, referred to as a GUI, is used to operate the machine. The majority of our software is written in Python, and the PyQt toolkit was used to develop the GUI. The software is responsible for interfacing with all electrical components and is relied on to control all the mechanical operations. Threading is used to allow multiple processes to run in parallel without the event queue lagging or locking up. A separate worker thread is used to handle the application programming interface with Gerbil firmware installed on the rail system microcontroller. Another thread is used to acquire and process images in real time, and we also use a thread to handle the torque control operations. The back-end software can be generalized in terms of 2 main control systems. That is, the torque control and alignment control. A major requirement is to accommodate a torque range of 50 to 360 inch-pounds with an accuracy of plus or minus 10% of the commanded value. To accomplish this, we use an Arduino Mega to run our control firmware. A motor controller is used to control the motor speed using pulse width modulation. A reaction-style strain gauge sensor is used to sense the applied torque, and an analog to digital load cell amplifier is used to provide a feedback gain. Our team attended Raytheon's metrology department to calibrate the torque sensor and verify our torque requirements. A GUI module was produced to improve the efficiency and effectiveness of the calibration and testing process. The sensor calibration was achieved by recording the raw sensor output along with its respective torque values measured by a metrology torque sensor. In result, we attained a linear fit with an R-squared value of 0.999, demonstrating the accuracy of the sensor itself. When testing the accuracy of the autonomous torque process, our system performed well, but only up until 135 inch-pounds. Past this point, the system produced an error outside the required range. This was a significant problem since we were required to reach up to 360 inch-pounds. We determined the inaccuracy was due to the rate of torque increase becoming too fast compared to the processing speed of the control system. To address this problem, we introduced both a hardware and software solution. In terms of hardware, we modified our analog to digital amplifier to improve the sampling frequency from 10 Hz to 80 Hz. For software, we made the speed of the motor be a function of the current torque state. We also began tracking the incremental change in torque per loop iteration. This value was used to introduce adaptive shutoff thresholding. In result, we achieved an accuracy well within plus or minus 10% of the commanded torque values across the full required torque range. The average and median error are both less than 2.5%. A graphical user interface offers a range of functionality for both operational and administrative purposes. A user can input a torque pattern by uploading a CSV file. Once a file is selected, the user can name it and add it to the list of existing patterns. When a pattern is selected, its contents shall appear in table form. If any edits need to be made, you can do so within the Edit tab. The torque operational path can also be viewed graphically. When looking to operate a torque pattern, the plate being operated on is not required to be set up in any particular way other than it needing to be within the designated workspace. Instead, a GUI module is used to define the plate coordinate system with respect to the machine's coordinate system. The offset and transformation matrix between the two coordinate systems is calculated by defining the location of two fasteners on the plate. In this example, we shall define fasteners 3 and 4. To accomplish this, the navigation controls can be used to position the gantry in the general proximity of the fasteners. Once the fastener is within the camera's field of view, it shall automatically be recognized and localized. This can be observed by noticing a bounding box surrounding the fastener in the camera's display. Once the Align button is clicked, the gantry will automatically align with the fastener. Then the position of the respective fastener can be recorded. The same process is repeated for the second fastener, and then the system is ready to operate. To achieve high accuracy in alignment, a deep network was trained using over 5,000 images to locate a fastener and the end of a socket bit. To improve computational efficiency, once the objects are located, they are cropped to the size of their bounding box and then passed through a series of convolutional operations. In result, several centerline approximations are determined. These results are then synthesized to determine the relative offset between the socket bit and fastener. The offset is ultimately used to determine the trajectory for alignment. In conclusion, our team has produced a system that can accommodate a torque range between 50 and 360 inch-pounds and achieve an accuracy of well within the bounds of plus or minus 10% of the commanded value. We have demonstrated our ability to align and engage with a fastener using an unsupervised machine vision system, and we have developed a graphical user interface that provides a functional and intuitive experience for the operator. Implementation of our design solutions at Raytheon is estimated to reduce production costs by $450,000 annually. Lastly, we would like to give a special thank you to our team mentor, Patrick Caldwell, and our project sponsor, Andy Harris. We appreciate all your support and guidance. Thank you.